Hey, take a look around you. No, seriously, right now. Look at the corners of your screen, the edges of the room you're in, maybe the design of a building across the street. It all seems kind of random, but it's absolutely not. It's all built on this hidden set of rules. And today, we're going to pull back the curtain on two of the most important ones, the simple, elegant concepts of perpendicular and parallel lines.
All right, so here's our game plan. First, we're going to go out and spot these geometric ideas in the wild. Then, we'll get into the nitty-gritty, defining and even building our own perpendicular lines. After that, we'll tackle the whole idea of parallel lines, and then we'll see what happens when we slice right through them. Trust me, it reveals some really amazing stuff.
So before we get lost in all the rules and definitions, let's just ground this whole thing in reality. Because geometry, it's not just some abstract concept from a textbook, right? It's the invisible framework that's literally holding our world together. I mean, just look at this bridge. You've got towers shooting straight up into the sky, cables crisscrossing at perfect angles, and that road running perfectly flat. None of this is an accident. The strength and honestly the beauty of this whole thing, it comes from geometry in action. It's all about lines meeting at perfect right angles and other lines running side by side forever, never touching. And that really is the big question, isn't it? How does all of this incredible complexity come from just a handful of simple rules? So let's stop just looking at the finished product and start digging into the how. We're going to start with one of the most fundamental relationships in all of geometry.
So our first big concept is perpendicular. The best way to think about it is it's the most stable, most predictable, most perfect way for two lines to ever meet. Okay, I know, the official definition sounds a bit technical. Congruent, adjacent angles. But what does that really mean? Well, all it's saying is this. When two lines cross, they make four angles where they meet. If all four of those angles are perfectly identical, then they have to be perfect 90-degree right angles. That is it. That's the whole secret to being perpendicular.
And you know what's so cool about this? It's not just some idea floating out there. We can actually build these perfect intersections ourselves, with nothing more than a compass and a straight edge. This is where we take the theory and make it real.
It's a classic four-step dance. You start with a line and a point just hanging out in space. Then you use that point to create two new points on the line. From those 2 points, you find a fourth point. And then, for the grand finale, you connect your first point to that new one. Let's see how it works.
So this first move is absolutely key. We put our compass point on P and just swing an arc so it crosses the line in two spots. We've just made points A and B. And the most important thing here is that they are both the exact same distance from P. That little fact creates the perfect symmetry we need for the next step. All right, now for the magic. We draw two more arcs, one starting at A and one at B. And where they cross, we get our new point, Q. Now think about this. Because of how we just made it, Q has to be the same distance from A as it is from B. This means the line connecting P and Q is perfectly balanced. When we draw that line, boom, it has no choice. It has to hit our original line at a perfect 90-degree angle.
And this isn't just some cool parlor trick with a compass. No, this is a physical demonstration of a fundamental rule of how our universe works. For any line you can think of, and any point not on it, there is exactly one line you can draw through that point that will be perpendicular. Not two, not a bunch, not zero, just one. This idea is what gives our geometric world its predictable, reliable structure.
Okay, so we've looked at lines that meet perfectly. Now let's flip the script and look at their total opposite. Lines that exist in the same space but are destined to never ever cross paths. Welcome to the world of parallel lines.
The definition sounds really simple, but it's super precise. There are two key ingredients. First, they have to be on the same flat surface. We call that coplanar. And second, they just never intersect. Ever. No matter how far you stretch them out into infinity, they just run alongside each other forever.
Yeah, this slide lays it out beautifully. Over on the left, that's parallel in action. It can be two lines, or a line and a whole plane, or even two planes. The rule is exactly the same. They never touch. Then on the right, you see the only other possibility, intersection. They cross, and their whole relationship is defined by that single point or line where they meet.
So remember how with perpendicular lines there was only one possible solution? Well, a very similar rule applies here, and honestly, this one is a massive deal. It's called the parallel postulate, and it says that if you've got a line and a point that's not on it, there is exactly one line you can draw through that point that will be parallel to your first line. This one simple idea
It's the foundation for pretty much all the geometry we ever learn in school. It's the linchpin that makes it all work.
So we've got these lines that never meet. Okay, but what happens if we just throw a wrench in the system and slice through both of them with a third line? Well, suddenly, that simple act, it's like a key, unlocking this whole set of hidden, predictable, and incredibly useful relationships.
So that line that does the slicing, it gets a special name. We call it a transversal. And here's where the magic happens. When a transversal cuts across parallel lines, the 8 new angles that pop up suddenly reveal this hidden, perfect order.
This little table here breaks it all down. See, we give these new angle pairs names based on where they're located. For instance, if they're in the same relative spot at each intersection, we call them corresponding angles. If they're on opposite sides of the cutting line and squeezed between the parallel lines, we call them alternate interior angles. And as you can see, each of these pairings has a very specific, predictable relationship.
Let's just focus on the 3 big ones, okay? First up, corresponding angles, the ones in the same position at each crossing. They're always identical, clones of each other. Second, alternate interior angles. Those are the ones tucked in opposite corners between the parallel lines. They're also always identical. The only oddball here is the same side interior angles. They are not equal. Instead, they're supplementary, which is just a fancy way of saying they always add up to a perfect 180 degrees.
And this isn't just a neat little pattern we noticed. It is a proven, rock-solid mathematical theorem. If you know for a fact that 2 lines are parallel, you can be 100% certain that their alternate interior angles are equal. This becomes an incredibly powerful tool for figuring out missing angles in all sorts of problems.
And here's the other side of that coin. Remember, supplementary means they add up to 180. So if you look at the 2 inside angles that are on the same side of that cutting line, you'll see one is an acute angle, it's small, and the other is obtuse, it's large. And that's the rule. You put them together and they will always form a perfect 180 degrees.
So we've just walked through the absolute bedrock rules for a flat, predictable world. That parallel postulate, the one that says there's only one parallel line, that's the key to everything we just saw. But it leaves us with one final, kind of mind-bending question. What if the surface isn't flat? What happens to our whole idea of parallel on a curved surface, like, say, a giant sphere? Well, that's where things get really weird, and the adventure of geometry truly continues.